Good afternoon. I'm Dimitris Kechrakos from the School of Pedagogical and Technological Education in Athens. And today I would like to talk about magnetic skyrmions on cylindrical nanotubes, formation, stability, and electrical detection. This is work we have done with collaboration of two students of mine, Lida Gianettou and Aris Patsopoulos from the University of Athens. A known issue of the application of skyrmions in racetrack memories is the skyrmion Hall effect that causes transverse motion of skyrmions across the nanostrip and eventually their edge annihilation. So the idea is to avoid this edge annihilation effect, to use samples with no free boundaries, like for example nanotubes. The points we address in this talk are first concerned with the possibility of stabilizing skyrmions on these cylindrical surfaces, what happens to their topological quantities, their geometrical characteristics, whether we can define a stability criterion for skyrmions, and if electrical detection is feasible. We understand that a basic ingredient of skyrmion formation on surfaces is the presence of Dzielosinski-Morilla interaction. This appears with two types, where the Dzielosinski-Morilla vector is either parallel or perpendicular to the bond connecting the two sides. In our case, that we are interested more in transition metal-heavy metal interfaces, the second is the case for the DMI vector, that we know that it leads to formation of nil skyrmions that have been thoroughly studied experimentally and theoretically. To answer the question about the formation of skyrmions and nanotubes, we have adopted a lattice model. So we start with a finite system of certain width and length, which is a planar lattice, and we gradually wrap this lattice around the cylindrical surface. As we decrease the radius of the cylinder, the two lateral edges of the sample come close together, and at the end, a nanotube is formed. So the curvature of the system can be characterized either by the radius of the cylinder R or by the central angle of the cylinder. On this lattice, we define a Hamiltonian or a total energy that is composed of four terms: the symmetric exchange interaction term, the antisymmetric one, which is the Dzielosinski-Morilla, a radial anisotropy term, and the Zeeman terms that comes from the externally applied field. To determine these lattice parameters, we assume typical parameters for the materials composing this nanostrip, which are typical of transition metal-heavy metal interface. We assume a grid size, we discretize it with a square grid, and we assume a grid cell size equal to 2 nanometers, and we end up with the parameters shown on the right. To find the equilibrium states or the ground state of the system, we use a simulation annealing procedure or field cooling procedure, if you want, employed using the Metropolis Monte Carlo algorithm with single spin updates and adaptive steps to accelerate the approach to equilibrium. So here are first results, some typical results from the study of samples of different sizes. So what we see in these color maps is the projection of the local magnetization along the field axis. And we have we present here two different samples, one with a small width and one with a big width. So when we start with a small sample, as you wrap it around the cylinder, we observe that the skyrmions on the sides become elongated, and when a nanotube is formed, the skyrmions disappear, cannot be supported on this small nanotube, but only stripes exist. On the other hand, if we start with a big lattice and we start deforming this stripe to end up with a nanotube, at the end, we have the presence of skyrmions on the front and the back part of the nanotube, but on the side, these elongated skyrmions, or worms as they call them sometimes, still exist. Now, if you look more carefully again in the last picture, it is clear that the presence of both types of, let's say, skyrmions, the circular ones and the elongated ones, coexist in this system. However, they are spatially separated. So this gives us the perspective that we can excite and propagate skyrmions along the ridge of the nanotube. Now, when it comes to quantify this picture we saw before, we calculate two topological quantities, the topological charge and the susceptibility. The charge is defined in the usual way, except that cylindrical coordinates are used instead of Cartesian coordinates. And we use an algorithm introduced by Berg and Lusser that transforms this continuous variable expression to a lattice expression. So what this expression tells you is that you have to triangulate the lattice and define the solid angles, calculate the solid angles defined by triplets of spins sitting on the corners of each triangle. So if you add up all these solid angles, you get the topological charge of the system. For a single skyrmion, this gives 1 as an absolute value, but there is a sign in front of 1, which is related to the orientation of the triangular contour. So depending if you travel around the triangle in the clockwise or anti-clockwise sense, you get plus or minus for the topological charge. The susceptibility is defined in the usual way through the fluctuations of the relevant quantity, the charge. And here are the results for different samples of different sizes. If you follow the blue line, we can see that if we start from the planar case, which corresponds to 0 angle here, we have the well-known skyrmion lattice, and the topological charge remains almost fixed up to a certain value of the critical of the angle. Beyond this angle, it starts to decrease. Looking at the color maps, we can see that at this angle, we start having deformation of skyrmions. Now, we understand this behavior in the following sense, that we know that for a planar case, there is a critical field below which skyrmions cannot be stabilized on the planar surface. Similarly, for the nanotube, in a homogeneous field, there is always a radial component of the magnetic field. So when this radial component becomes lower than the critical value, the skyrmion becomes destabilized. It's elongated and then it disappears. From this argument, we can calculate the critical angle for a nanotube, and actually this agrees with the value we find in the simulations. Second, it's interesting to see that for the case of a nanotubes, whether it is a large or a small system, the topological charge is always 0. Examination of the color maps shows that you have skyrmions on the front and the back part, as we also saw before, but they have different projection. The magnetization has different projection of the radial direction. To understand this behavior, we can look at this one-dimensional analog. If you have a planar case and you have two skyrmions formed on this surface, which both have clockwise chirality, if you bend this surface and you still apply the same field as before, then the same skyrmions occur. But when you calculate the topological charge, in the first case, both have +1 topological charge, so in total 2. But in this case, the topological charge of the lower skyrmion is -1. So if you add the topological charge, you get 0. So the topological charge is not really a good quantity to calculate in the case of a nanotube where you have surfaces of opposite normal direction. I forgot to say before that the critical angle at which the topological charge starts decreasing is associated with a jump in the susceptibility. But this is not really a true phase transition, because on the right-hand side of the jump, you have a mixed phase of skyrmions and stripes. So it's not a clear, pure phase. Finally, it's interesting to see what happens if you apply a radial field. In this case, the skyrmions do not deform substantially. The topological charge is well preserved. And that would be an ideal case to use if you want to have a skyrmions in a nanotube. Now, coming to the geometrical aspects, we have analyzed the shape of the skyrmions by digitizing the color maps I showed you before and attributing 0 and 1 to the intensity inside the core and outside the core of the skyrmion. For each compact shape, corresponding to a skyrmion, we can define two invariant moments, circularity and linearity. The circularity becomes 1 if you have a perfect circle. The linearity becomes 1 if you have a perfect line. So by looking at the values of these two quantities, we can deduce about the shape of the skyrmion. Also, we have calculated an effective radius, which is twice the radius of gyration, and it coincides with the actual radius of the skyrmion if this is circular, and it gives a value between lower than the radius if you have something which is not circular. And here are the results for a system, a planar system that hosts initially a single skyrmion. What happens when you start wrapping it around a cylinder? We can see that initially the shape is preserved, but above some angle, the skyrmion weakly deforms and then annihilates. If you follow the values of circularity and linearity, we can see that circularity remains almost constant around 1 below this angle where deformation starts, and the linearity has very small values except for a small hump near the angle that deformation occurs. So this picture is quantified nicely with these two moments of these invariant moments. Also, we have calculated the effective radius, and we found that for very large cylinders with very large radius, the effective radius remains constant. When the radius of the nanotube decreases and becomes comparable to the radius of the skyrmion, then the skyrmions annihilate. So from this graph, we can deduce a stability criterion that relates the two competing geometrical lengths of the system, the skyrmion radius and the nanotube radius. We can summarize our results for different materials by looking at the phase diagram. We've plotted the field versus the anisotropy of the system. This defines a pocket inside which skyrmions survive and outside which skyrmions are not stable. And what we observe from this graph is as you increase the curvature of the system, you require stronger and stronger fields to stabilize the skyrmions. Finally, we have looked at the electrical conductivity of this system by attaching two electrodes on the left and the right of the system, and described the electronic structure of the system by a simple type binding Hamiltonian, extended by a spin scattering term whose strength depends on the relative direction between the local moments and the electron spin. Using a standard Landauer formula, which is valid for low bias and low temperature, we obtain the thermal evolution of the conductance of the system as you decrease the temperature. And we can see that when skyrmions start to form in the system, there is a jump of, well, a continuous and abrupt increase of the conductance. This happens both for the planar and the nanotube case, and it's an indication that the system makes a transition from the fully disordered case in terms of spin to an ordered case. Looking more carefully at the planar case, we can see that because of thermal fluctuation, different samples in the stable state can have different number of skyrmions. So examination of the values of the conductance at the lowest temperature helps us to correlate the number of skyrmions in the system with the conductance values. And we can see there is a monotonous behavior between the two. As the number of skyrmions increases, the conductance drops. However, this is not the case for the nanotube. And this is because here you have a mixture of skyrmions and stripes. So it's not easy to relate the number of skyrmions to the values of the conductance of the system. With this, I conclude, and here are basic, our central conclusions, which are the following: that the nanotube radius has to be larger than the skyrmion radius if skyrmions are to be stabilized on nanotubes. The circular shape is preserved in the stability regime. Skyrmions coexist with stripes on a nanotube, but fortunately they are spatially separated. Stronger fields are needed for smaller radius nanotubes, and a cylindrical field would be the ideal case to stabilize a pure skyrmionic phase on a nanotube. However, we understand that this is technically difficult. As regards the electrical conduction, the electrical conduction measurements can reveal the transition to the skyrmion phase, but only for the case of planar strips, we can correlate the values of the conductance to the number of spins. Finally, work on the topological Hall effect on this system is in progress and will give us more information about the skyrmion phase. By closing, I would like to thank the Special Account of Research of ASPETE for financially supporting this work, and the State Scholarship Foundation, and of course you for your attention. Thank you very much.